It's my pleasure to introduce Nadia Drenska to you. She finished her PhD at the Theorem Institute at the New York University and is currently a postdoc with Jeff Calder at the University of Minnesota. The stage is yours, Nadia.
Thank you. First, I would like to thank the organizers for this opportunity to speak. I'm very excited I could do that. So thank you. I'm Nadia Drenska, and I'll talk to you about the PDE interpretation of prediction with expert advice. This is joint work with Bob Cohn at the Grant Institute and Jeff Calder at the University of Minnesota. Okay, so let's get started. So here's the outline of my talk. I would introduce the general framework, and then I'm going to talk about the problem today, the history-dependent problem. And there are two approaches to that. The first one was developed with me and Bob Cohn, and the second one was developed in collaboration with Jeff Calder. And then I'm going to conclude. Okay, so what is prediction with expert advice? Basically, it's a very old problem from online machine learning. Online machine learning refers to the type of machine learning where new information comes available in many states and you need to react to that. So in this particular case, we're given a stream of data and a pool of experts, and they're trying to predict what happens with the pool, with the stream of data. Then we also have a player, and the player uses expert advice to make her own prediction. And the way we measure the performance of the player is to look at the difference between an expert's performance and the player's performance. So that would be our state variables. Okay, so in our particular setting, we're using a worst case analysis. So oftentimes there are assumptions on the data stream that it's probabilistic, for example, but we are not in this regime. We're working with a situation where the data stream is controlled by the adversary, and then the player is trying to play against the adversary to minimize her regret, and the market is trying to maximize that regret. So this is a two-player zero-sum game. Some notable applications are weather prediction, click prediction, algorithm boosting, and financial math. Okay, so let me give a motivating example as to why we care about prediction with expert advice. Say every morning you wake up and you try to figure out whether it would rain or not. And you have a lot of possible sources which you could use to make your decision. And some of them are supposed to be more accurate, so those would be some weather websites. And then there are some experts which are kind of silly, for example, saying that you could toss a coin and see whether it comes heads, and that would tell you whether it rains or not. So clearly, there are a variety of possible experts you could use. And what we're going to try to do is to figure out as you go which experts are better and try to listen to the ones that are better to inform your decision. Okay, so here's a slide for previous work. So in machine learning, typically, the algorithms that you obtain are in a regime where you have a very large number of experts, and they try to focus on broad cases of, they try to focus on cases with many experts where the strategies are not necessarily really tailored to the regime that you're working on. So you would get general bounds O of square root of n, but that might not necessarily be the optimal strategy. Those are just strategies developed for a broad class of problems and not necessarily about the particular problem that you're solving. So in the randomized strategies problem, this has changed. There are instances where you're solving the problem with a small number of experts instead of a large one, and then you're obtaining more accurate bounds on the regret. And then recently there have been PDE approaches to the randomized strategies problem on which I've also worked. Okay, so we're trying to figure out the optimality in the general setting of n experts. So for the first part of the talk, we would focus on 2 experts, and for the second part of the talk, we would focus on many experts. So here's a motivating example. Why do we care about history-dependent prediction? So suppose that we're playing a baseball game, and then there's a main defender called the starting pitcher who plays every 5 games. And then we assume that the rest of the defense plays daily. So we will have a stream of data, which is whether the team won or lost. And that stream of data would be dependent on what happens every 5 days, because the main defender plays every 5 days. So you want to incorporate that in your algorithm. So what happens is that as a gambler, you try to listen to the betting sites and to combine their predictions to form a prediction of your own. And the question is, how do you bet over a very, very long period of time? In this case, 162 game season. Okay, so here's the problem for this talk. It's called the history-dependent problem. It is a 2-person zero-sum game. We have an adversarial market who controls the stock. We have states of historical data where we record what happened over the past D days of data. So depending on whether B is +1 or -1, the stock would move from one data state to the next by forgetting the oldest D+1 information and focusing only on the past D. So for example, if this is a time state that we care about, it says yesterday there was a 1, so the stock went up. The day before, the stock went down. Then, went up. Then 3 days ago, the stock went down, and so on. And this state moves to either M+ or M-, which encodes whether the stock went up or down. Those states would turn out to be very important throughout the talk. Okay, so aside from the market, we have time-dependent experts, which make predictions through algorithms that depend on the time states. And then at every step, we have an investor who buys or sells F shares of stock. As we said before, regret is the difference between the best performing experts and the investors in the investor's game. Because we're working with the linear regret, the way that regret is accumulated is you look at the difference between an expert's prediction and a player's prediction, and you multiply that by -1 or 1, depending on whether the stock went up or down. Okay, so the overall question we're trying to answer is that if we have a final time in a history state, what's the best strategy for us so that we guarantee the least amount of regret? So the regime that we want to solve this, as I said in the beginning, is for 2 experts in the beginning, in the first part of the talk, and for n experts in the later part of the talk. Okay, so After n steps of the game, we accumulate regret as follows. We look at the one-step regret. And after k steps, we sum the regret over the past n steps. So the goal for us is to look at a function which involves the regret accumulated so far, is to maximize, the market is trying to maximize this function GFRN, and the investor is trying to minimize. So in the classical choice for machine learning, GFX is the maximum of all regrets. So R sub n is a vector which records regret with respect to each expert. And that's recorded in variables x1 through xn. And then the reward function is looking at the maximum of those. So GFX would be our measure of performance. It's looking at the largest regret with respect to the best performing expert at the final time t. Okay, so there's a few assumptions on the payoff function. Those are assumptions that we will need throughout the talk. Some of them could be relaxed, but I would just stick to those. In particular, one of the assumptions is that we have a smooth payoff, C4, which is something that we need for some of our theorems, but similar results hold when the function g is just Lipschitz and not C4. Okay, so let's look at the value function. We have this function g of Rn that we defined. And then we ask ourselves, what's the regret that we accumulate if both the player and the adversary were playing against each other over many terms? So one way to look at that is to say, okay, the best that could be done after one time step is a min-max between the player's performance and the market's performance. I use market and adversary interchangeably. So we have a min-max of the function of the reward function g, and that min-max reflects what happens over one time step. But suppose we look at two time steps, then we will have a min-max of the following expression. And we can basically iterate that to obtain a value function which is defined recursively through min-maxes. So one way to rewrite this function is through the dynamic programming principle, which says the best that could be done today is a min-max of what could be done tomorrow. So that's why we have just one min-max relating the time steps right now. So m would go into m plus or m minus, depending on whether the stock goes up or down. And then x would move to regret for one day, which is the difference between q and f, multiplied by the sign of the stock, plus 1 or minus 1. Okay, so once we have this dynamic programming principle, we can talk about what happens when we want to scale this regret. So basically, since we're interested in many time steps and we have an iterative process over many time steps, we define the following value function. So we will have our value function scaled with epsilon in space and epsilon squared in time. So the analog is if you were to have a Brownian motion and I'm sorry, I'm forgetting the word, but if you were to use Brownian motion and random movement, then the following scaling occurs. X is scaled with epsilon, and epsilon squared is the time change. So the question is, what can we say about u epsilon as epsilon becomes small, which is the equivalent to what can we say when the time steps n go to infinity. So looking at this dynamic programming principle here and the scaling over here, we rewrite the dynamic programming principle for the function u epsilon. Okay, so let's look at what happens with time states. So suppose that there was only one day of data that we were recording. So suppose that data was either -1 or 1. Then if the stock goes up, we move from -1 to 1. And if the stock goes down, we move, and the past history state is 1. Then if the stock goes down, we move from 1 to -1. And if the stock goes up, we still stay at state 1. So movement along this graph would be very important, because we would, our dynamic programming principle is related to what happens as time states change. Our value function over here had to do with what's the regret that will be accumulated if we had regret x, we were at time t, and the history state was m. And that would be the optimal regret that would be accumulated if the stock went up. And then compared to the regret that would happen if the stock went down. So we obtain for different values of the number of days that we care about, we obtain different graphs called de Bruijn graphs. And for one time state, they're quite simple, as you can see. But for two time states, they become more involved and then more complicated. So suppose we're looking at the d equals 3 days of data. Say we're at state 100, which says yesterday the stock went down, the day before it went down, and the day before it went up. If the stock goes down, then we move from 100 to 001, because we forget the latest times, the most, the oldest time state. So the idea is that we have regret, and based on the states M, regret accumulates differently. So as we move along the graph by tracing time states, we have different accumulation of regret that comes from every vertex. So the idea is that through the dynamic programming principle, we can see how regret accumulates by moving between two time states. And if we iterate that, then we see that the value function that we obtain is associated to a random walk, to a walk on the graph. And it's not a random walk, it's an adversarial movement, because the market is trying to make the process accumulate the most amount of regret possible. So then the player is trying to choose such investments so that he accumulates the least amount of regret possible. So there would be choices of F, such that if we can make it so that all possible cycles on the graph have the same average rate, then the investor would be indifferent to what the market does. So the optimization between the player and the adversary is such that we need to optimize along the graph. Okay, so let's employ a very important tool in our analysis. It's Taylor expansion. What we assume is that the value function that we had, since it occurs over a very long period of time, we assume that it forgets the initial time state m. And so we assume that all functions u epsilon with any time step n look like a smooth function. We will justify this claim later. But for now, we make this assumption and we try to see what happens. So u would be the min-max of x plus the movement delta x. And then, so we use the dynamic programming principle to establish this fact. And then we Taylor expand the function inside the dynamic programming principle. And we obtain the following expression, u at xt plus epsilon terms plus epsilon squared terms. We can observe that u cancels out. And then we have a regressive accumulation of order epsilon and of epsilon squared. So since epsilon is very small, the regret accumulation times epsilon is the leading order one. So the market would try to make this expression as large as possible so that there's the most amount of regret accumulated, versus the player would try to minimize that. And since the market can control the sign of this expression, the optimal thing for the player to do is to cancel this expression out. So when you rewrite this, you see that the investment f is actually the ratio of these derivatives. And with that choice of f, then regret accumulates of order epsilon squared. So if you look at the epsilon squared expression, it says that u sub t, the time derivative, is proportional to the following expression. And the idea is that if we have many time steps, then we will have averaging. Why is that? Because ut here is proportional to a function of n, and we're trying to average out over many time steps, which means that m changes as I explained along the graph. Okay, so let's make a correction to f. So we observe that the first order term of f was the one that canceled the epsilon order term, but we still have remaining the second order term. So we add a correction of epsilon times f sharp, and that correction will correction would influence this expression. So we obtain that following expression, ut plus a function proportional to the Hessian gradient squared u, and then minus this investment f sharp. So f sharp is something that the player chooses. So the question is, how can the player choose f sharp so that the accumulation of regret is the smallest possible? And know that f sharp would be something that we choose on every vertex. And so the question is, what's the least amount of regret over a very long period of time? And then in order to figure out the optimal strategy, in the first part of the, in the first paper that I worked on, the first part of the talk, one will solve a linear program. And the idea is that when we solve a linear program, if we can choose f sharp to be such that regret along all cycles is the same, then it doesn't matter what the adversary does. There's one and the same accumulation of regret on average. So this means that the player has done the best possible for her. Okay, so here's the main result from the first part of the talk. Let us have you satisfy the following PDE, which could be rewritten through in this form. And so let's look at the average regret on the graph. The average regret on the graph is just the sum of the regret over all states divided by the number of states. And here we see that the regret is, in this particular case, regret is proportional to the difference between what the experts say squared. Recall that Q1 was the prediction of expert 1 and Q2 the prediction of expert 2. And so we obtain the PDE above. And what's important about this PDE is that it's very close to the optimal solution for the discrete problem. So when I was defining U epsilon was the optimal investment. I'm sorry, it was the optimal regret accumulated if both the market and the player were playing the optimal for them. And what this theorem states is that the difference between that regret and the regret accumulated from the PDE is small for their epsilon. This holds for 2 experts and at most 4 days of data. We have a conjecture that this would hold for any number of days that will have a linear rate. And in the second part of the talk, I will tell you about what happens when we have any number of experts and any days of data. We'll have, again, convergence, but with different rates. Okay, so as I said, F sharp comes from a solution of a linear program. So we don't have a closed formula, but we will produce another closed formula, which is asymptotically optimal, just like this one in the second part of the talk. Okay, so in the general case of n experts, we have an average over what happens over regret over each time state. So we have ut plus this average is 0, where the values eta are of this form. This is basically the difference between the experts regret, between the experts prediction and players prediction. This expression here is what we call F2 leading order term. Okay, so basically what's important is that we have n experts and we have a PDE associated with those n experts. So we will have a similar theorem that relates the PDE with the discrete solution of the value function. So a key observation in the second part of the talk is that instead of working with the one-step dynamic programming principle over here, we work with the k-step dynamic principle over here. So what this says is the optimal thing that I do today is the optimal thing that could be done tomorrow, and the optimal thing that could be done the day after tomorrow, and so on. We iterate the dynamic programming principle, this one, into a dynamic programming principle later on. And as you will observe, the time state M changes, so we keep on adding the values of whether the stock went up or down. Okay, so similarly to what we did with the one-step dynamic programming principle, we Taylor expanded it, and what we do in this expression is we write the dynamic programming principle for k steps, and we Taylor expand it again, and we obtain the following expression. We call this expression the local problem because it has to do with local asymptotics. So what we can show is that this this expression called the local problem is actually a sum of products of the second order derivative times the changes eta m, where eta m was the investment of the of an expert minus the investor of the minus the investment of the player. So one thing to note is that zeta m accumulates as we move along. The local problem regret accumulates proportional to zeta, and we average this out over time steps to obtain what the local problem accumulation is, what the accumulation corresponding to the local problem is. Okay, so let me try to explain how this all works. So suppose we were at time state 101. The way that the regret accumulates is we look at the two possible states that regret can reach. So starting at 101, we would move it either 010 or 011, forgetting the first digit 1 and appending digits 0 or 1. And then we look at the next time state, which is again corresponds to two possible movements of the stock, and so on, so we obtain a tree. So when we're trying to figure out what's the regret accumulation zeta, when we unravel this, we see that it's related to the average of zeta over the next nodes, which is the average related to the average of zeta over the next nodes, and so on. And the idea is that because of the structure of our tree, after D days, we will have forgotten the information that came from the D days worth of data that we started with. So after D days of data, we will actually have an average over the entire tree. Because as you can see, so starting with 101, we, after 3 days of history, we reached a place where we're actually averaging out over all possible time states. So basically the next problem is that the regret accumulated through the local problem minus the regret that we accumulate by moving along the tree is actually very close. Okay, so here's the main theorem of the second part of the talk. We choose any number of experts, and we also choose G to be uniformly continuous. It's not necessary that it's C4. Then what we obtain is that the amount of regret accumulated through the discrete problem converges to the amount of regret accumulated with the continuous problem. And the two are very close. If we have that G is C4, then the difference between the discrete regret and the continuous regret is proportional to n to the negative 1/6, where n is the number of days played. And we have a similar result that holds for just Lipschitz functions. Okay, so finally we obtain the following optimal strategies. The optimal strategy at time Lk plus I is proportional to the first order regret that we had, the inner product between the vector of first derivatives times the regret with respect to each expert times the each expert's function of regret. And then we have epsilon order terms. And then again, in the denominator, we have the vector of derivatives of the with respect to each expert's times 1. So we just have a sum of the derivatives, just like in the previous, just like in the guess that we had for F. And then we have an epsilon order correction. Okay, so as a conclusion, we solve a problem from online machine learning using viscosity solutions of PDEs that I didn't really emphasize, but we have solutions of PDEs and we have ideas from optimal control theory. Since we have an iterative process with decision making at every turn over a very long period of time, it makes sense to use continuous techniques to try to answer this discrete problem and to figure out what the optimal strategies are and what's the regret function. The goal of this analysis was to understand the optimal decisions over a very long period of time, which we do using scaling limits. And one can observe that the way to do this was to use discrete formulation and a continuous formulation. And the discrete formulation was a numerical scheme for the PDE that I showed you. Okay, thank you for listening. With that, I will conclude.